We are delighted to have as a guest speaker this evening, Mike Carroll. He is an author, artist, and international lecturer. His articles and paintings have appeared in hundreds of magazines, including National Geographic, Smithsonian, Astronomy, Sky and Telescope, Ciel et Space, a French magazine, Time magazine, and many others. In the 2015-16 season, Mike explored Antarctica's active volcano, Mount Erebus, to study the analogs of ice moons in our solar system. One of his paintings in digital form is on the surface of the moon. On the surface of Mars, aboard the Phoenix lander, which landed on Mars on May 25th, 2008, about 16 years ago. Mike is a fellow and founding member of International Association of Astronomical Artists, also a member of Science Fiction Writers of America, and a recipient of the Lucien Rudaux Award for Lifetime Accomplishments in the Astronomical Arts. Mike has written over 30 books and lots of short stories, I understand, on various topics like ice moons, Antarctica, exoplanets, outer solar system, and going back to moon. And his latest book is Planet Earth, Past and Present, Parallels Between Our World and Its Celestial Neighbors, published last year. So please welcome Mike Carroll.
Okay. So, Mehmet, thank you so much for the introduction, by the way, and Earth of, Planet Earth is the book that I'll be talking about a little bit tonight. If you're interested in seeing more paintings from it or reading a bit more in depth about some of these things I'm touching on tonight, you can pick one up over there. Also, this should be entertaining because in the last 8 days, I have had about 30 hours of sleep, which is about 4 hours per night. And so if I don't make sense on some point, just stop me, okay? And I'll say it again in a different way. And it'll probably still be wrong, but that's okay. We'll go with it. So, alien Earths from hell to paradise and back again, we'll see. It's interesting that our planet is not the planet it was, and it is not the planet it will be. The Earth throughout time has resembled other worlds around us. At one time, we had a lot more carbon dioxide and higher pressure, a little bit like Venus. We have had snowball epochs where the environment here was a little bit more like Mars. Lower pressure, higher CO2, very cold. Not as cold as Mars, of course. It may seem a stretch to compare Titan to a past Earth, but in fact, the chemistry going on this planet-sized moon at Saturn is in some ways similar to the prebiotic chemistry that was coming together here on Earth a long time ago. So who knows what's going on Titan? We'll just have to explore and see. So the Earth, as we look around at other worlds, and you all know this very well, the Earth is a unique world. All worlds are unique, but the Earth has a long list of things that set it apart from other planets. The type of galaxy that we are in has to be just right for terrestrial planets of the type that we are. It appears now that there's a habitable zone within the galaxy. The Earth is right smack in the middle of that. We have the just right star, of course, our sun, which a lot of you saw in eclipse recently, is a very stable star. It's been the way it is for a while. Size, temperature, age, all these things contribute to why the Earth is kind of fine-tuned for life here in this environment. We're in the zone, we're in the habitable zone, the Goldilocks zone, as they say, just the right distance from the sun for liquid water to exist on the surface. Now, of course, as we have studied moons of the outer solar system, we realize that the habitable zone may actually stretch much further than we initially thought, because there are oceans of liquid water out in the outer solar system. They're just encased, they're capped by ice. But great place to look for life. We have an asteroid shield in the form of a gas giant at just the right distance from the sun. Jupiter tends to preferentially cast asteroids out toward the outer solar system. It clears the inner solar system of a lot of stuff. So we have a lot less battering going on here than we might. And we'll see in a moment why that is so significant. We have a robust magnetosphere that gives us a nice shield. Some exoplanets orbit very close to red dwarf suns, which are nasty in terms of radiation. But if these are super Earths with a big enough core, they may generate enough magnetosphere to protect themselves even in that environment. So we're still parsing out what a habitable zone really is. And then finally, of course, well, second to the last, we have just the right moon. You all know all the great things that the moon does for this planet. Plate tectonics and volcanoes recycle our atmosphere and our minerals. You don't have active volcanoes everywhere. There are a lot of them in the solar system, but plate tectonics are rare. There are, and we'll talk about that in a minute. So, location. Any realtors out there? It's true for planets just as it is for real estate. Whoops. The Earth and the other terrestrial planets formed close to the sun, where you've got a lot of heavy materials, minerals, metals, and rock. That's why these planets are the way they are. The frost line is out to about in the asteroid belt. So beyond that, you can have a lot more volatiles in a planetary environment. But the Earth is in a spot that the reason the Earth is the way it is because it formed within this region close to the sun. And as it did, things were just a mess. There was stuff flying around constantly as planets grew, as asteroids grew into planetoids. They bashed into each other. It was a lot like a cosmic bumper car. There were planets that almost formed that were destroyed many times over. And in fact, we saw an echo of that later in Earth's history, which we'll see in a minute. Early on, there were some parallels between the Earth and other worlds in terms of incoming asteroids and comets. This is Mercury. There never was much of an atmosphere on Mercury. Okay, it's always been essentially an exosphere. There may have been a bit of a primitive atmosphere, but the pressure was very low, not enough to slow down much of the incoming stuff. But there was volcanism, and when you get a volcano in a vacuum, as we've seen on Io, Jupiter's volcanic moon, you get these big umbrella-shaped eruptions. Well, on Earth, the same thing was going on, but we had a whole lot more atmosphere to buffer us from all those incoming rocks and metal chunks. And so the Hadean age on Earth looked a bit like Mercury for a little while. But then things settled down. Things cooled off, the Earth stabilized. It may have actually had an active water cycle. So there was rain cooling the surface, and all was great. The birds were singing, the sun was shining. Well, maybe not then, but then something big happened, and they call it Theia. Not an official name, but this was a planet Mars-sized or possibly even larger impactor, a protoplanet that came zooming in from the solar system, possibly close to the Earth's orbit for a while. So the impact speed may not have been as big as people initially thought, but this thing came in, hit the Earth, and peeled off the lighter stuff in our crust, which became a ring of debris. And within about less than 20,000 years, that ring coalesced into the moon. This was a great theory for a while, but there was no way to prove it until we had bits of the moon in our hands. After Apollo, we began to see patterns within the minerals of the rocks that indicated that this scenario probably did play out. Also, compare the spin rate of the Earth to that of Venus, our twin sister. Venus is very, very slow. The Earth spins very quickly for planets of this size. What may have happened was that we were spun up by this impact. And in fact, the dynamics of that kind of glancing blow fit with a lot of the mathematical models of the Earth's spin even today. So here we are, maybe 100,000 years after that nasty day. Things are calming down again. We have lava coming out of the rocks still, but we've got a new water cycle. So the Earth is moving toward becoming the planet that we know today. But there was a long ways to go. All kinds of things happened along the way, bumps in the road, major extinction events. You can see the red lines throughout this image are extinction events. And of course, the most famous one is the terminal Cretaceous event at the end of the Mesozoic, the end of the dinosaur age. Many of these extinction events may, although some are very tentative, may have been linked to impacts. Not all of them were. And it's hard to tell from the record, and there may have been climate change due to other things. There are a lot of things that can wipe out life, but impacts may have played a significant event in the path of our planet. That one that came in at the end of the dinosaur age left a crater at the very edge of the Yucatan Peninsula. The ocean is to the north, and you can see a ring of limestone that's stretching across the Yucatan Peninsula. And in fact, that limestone eroded into cenotes, which formed the backbone of the Mayan civilization. They depended on these things for a good water supply. So in a way, the big rock that killed the dinosaurs off actually gave rise to the Mayan civilization. We're not sure, but there are some theories about what the dinosaurs thought of this event. This is my reconstruction. This is science. This is science. Good science. So on to Venus. the planet we do not want to become. It's an exotic, wonderful planet. There are all kinds of great things going on here. Sadly, we've been ignoring it with our spacecraft, but that's about to change. And it turns out, and we've known this actually since about 1978, Venus likely had oceans, possibly even more extensive oceans than the initial ones on the Earth. We know this because of an isotope called deuterium, heavy hydrogen. There's a bunch of deuterium that's floating around in the atmosphere of Venus, which means that there used to be more hydrogen in the system, and hydrogen is a marker for water, of course. So it does appear that Venus was a very, very much more Earth-like world for a little while than it is today. But today, it's a pretty nasty place. And we visited the surface several times, gone through with atmospheric probes, and it brings up a big mystery. One of the greatest mysteries of planetary science. It's called the 12.5 kilometer Pioneer Anomaly. We can all say it together. No, that's not. So here's what happened. Several of the Soviet landers, Veneras, as they descended through the atmosphere of Venus, when they reached about this altitude, they had system-wide failures, electronics, communications, but then they recovered as they continued to descend. They call it the Pioneer Anomaly because all four atmospheric probes that Pioneer deployed into the atmosphere of Venus suffered similar failures, sporadic failures, at exactly the same altitude. Now, NASA did a study a few years ago and decided that the Pioneer probes had some insulation on them that was not tested correctly in the environment chambers, and it melted and shorted out stuff when it got to the right altitude. That does not explain, though, why a host of Soviet and Russian probes have suffered the same thing. Very mysterious. It turns out that at about this altitude, metals, certain metals, can vaporize at the ground and rise up along the mountains, just like water does in the foothills out here, okay? What happens to the water when it goes up the mountain? Yeah, it condenses, it freezes, okay? Well, if you have iron pyrite that is drifting up the mountain, it's going to condense at about 12 kilometers altitude. And in fact, that's what we see in these radar bright areas. We see some kind of metal. We don't know yet which kind. There's a bunch of candidate metals it might be. But it's possible that these probes went through a layer, a haze layer of metal vapor, and that's what scrambled their little minds. So it may be that as you stand on the surface of Venus, looking at the mountains, you would see fool's gold rocks. Wouldn't that be beautiful? The solar system just continues to surprise. I love it. So here is an accurate rendition of Mars. Actually, we have been creating planets in our own image for a long time. Here, of course, is, who is this? Yes, absolutely. Good old Percy. And of course, he drew a lot of highly detailed maps of canals. He was not the only person seeing them. Lots of people were seeing them. If you look through a telescope at Mars, you see patterns, right, in the dark areas. It turns out that these patterns are mostly drifting volcanic sand, essentially, dark sands. But we like to think of planets as Earth-like. And Mars was very exciting to people on this count. But then finally we got there with spacecraft. This is a Mariner 4 image, and it was a shock. How many people here can remember the Mariner 4 mission? Okay, it was fascinating to watch the scientific community. They were baffled. There were very few people who predicted craters on the Martian surface. There were some. But it turns out that at first we thought Mars was very moon-like. Then the Vikings came along and Mariner 9 as well, orbited and began to give us more detailed images. This one, of course, proves that there's alien life. You can see that face sculpture there. It's very nice. These days we're getting much more detailed and magnificent images. Every day you can get online and see new images from Mars and get weather reports. It's just amazing. And it's an international game now, which is lovely. United Arab Emirates sent the Hope mission. This is from that orbiter. Very nice images coming back. But Mars has some interesting parallels with the Earth as well. This is a rock glacier in Canada. Okay, you can see the stone has kind of come down and covered over the ice, but there's still an active glacier underneath. And it turns out that Mars has a lot of places that look like active rock glaciers. Now, we don't have good enough data from these spots yet to tell if there's really water ice underneath that stuff, but it sure looks morphologically like a glacier with a tongue, and the only question is if it's still alive today. So all that leads us to an interesting mystery of the Earth. We look at the Earth and there's something missing. Something that may have to do with glaciers. In fact, there's 1 billion somethings missing, 1 billion years of stratigraphy have disappeared from part of the fossil record here and there, okay? Where did it go? It's called the Great Unconformity. You can see it very well in the Grand Canyon. Up at the top here, everything is nice and neat and in layers. I mean, things are jumbled up a little here and there, but you get down to this layer, and all of a sudden it doesn't make sense for a while. There is missing layers, 1 billion years worth. And in place of those, there is essentially talus. There's stuff that is very typical of glacial erosion. So it looks like glaciers had something to do with wiping out all these layers of recording for us in the rocks. And in fact, it turns out that the Earth has gone through several events called snowball epochs, where ice made it all the way down to the equator. The entire planet was encased in ice, probably very little open water in the ocean. This happened twice at least. We have good records for 2 times. This is a painting I did of the breakup of Rodinia, the supercontinent, and here are some. So this painting is kind of partway down. To give you some idea of the timeline, Copernicus came along about 800 million years ago. Tycho was about 108 million years ago or so. We think that these 2 snowball events happened at about 730 and 680 million years ago. Climate has changed on this planet for a very long time. At about that time, there wasn't much oxygen in the atmosphere at all. There was free-floating iron in the oceans. It would have turned the water a rich green, a very strange, verdant ocean around us. And at this time, or even before it, we begin to see in the fossil record early life, ancient, simple things. Stromatolites there on the right are living stromatolites in Shark Bay, Australia. At about that time, or the early time, we see banded iron, iron locked into these rocks before there was oxygen in the atmosphere to turn it into rust. So all this adds up to one important fact. Venus and Mars have atmospheres made mostly of. Huh? No, methane's in the outer solar system mostly.
Carbon dioxide.
Carbon dioxide, yes, there is some methane on Mars though, yes. But CO2 is what rules the terrestrial planets, at least it should. But the Earth is the outlier. We've got mostly nitrogen, a little bit of oxygen, okay? And then some trace gases that are giving us some problems these days. So Earth is, again, a unique world and intriguing, and all the differences that it shows tell us something about what's been going on here in the past. One thing that sets our planet apart, I mentioned this before, plate tectonics. This was the very first world map showing the ocean floor, and it was largely guesswork. They had about 12% of the ocean floor mapped at this point. And it's not much better today, actually, although they're doing a concerted effort to map the entire world. You can see in the magnetic fields of the rocks how the plates have moved around, how they pulled apart. If you look here off the coast of Iceland, two plates are pulling away from each other, and you actually see a mirror image of the reversal of the magnetic pole in the Earth's magnetic field as you look across those the sea floor where it has spread. Now, in the lower left is a little map of Mars with some magnetic field data. And one theory is that we're seeing a little bit of that, hints of that, in the Martian magnetic field. It may be that there were some rudimentary plate tectonics really early on Mars. There is a very recent paper that kind of contradicts this, and so the jury's still out. We'll just have to see where this goes. We need more detail, more data to really know. And now we come to one of my favorite places, although I haven't actually been there, Titan, the planet moon. It's the second biggest moon in the solar system, about as big as the planet Mercury. It has more atmosphere than a fancy Italian restaurant. It's a spectacular place. Let's have a look-see. In fact, of all the terrestrial light worlds, the worlds with solid surfaces, Titan is second only to Venus in atmosphere. Mars has 0.006 bar. It's equivalent to the Earth at 100,000 feet. Okay, here's the Earth. We know that there's more than one bar here. I mean, there's a couple just down the street. But Titan has 1.5 times as much air as we do. So fascinating world, low gravity, lots of pressure, perfect place to fly. It rains methane there. The mountains are water. So the Earth has rain and mountains, but they're made of different things. So Titan is a fascinating world with great oceans, seas of liquid methane. In fact, the biggest one is equivalent to the Black Sea in area, Kraken Mare. But what is interesting to astrobiologists is the coming and going of these lakes, because current theory says that tree biology starts in places where you've got little fractures like this, where the surface kind of cups, okay, so that you can have moisture that stays in that little cup. But what you have to have is drying and getting wet again to mix the chemistry. And that is what has happened in a lot of these lakes. You can see paleo shorelines around some of the lakes, many of the lakes on Titan, where there's kind of a bathtub ring. This is Lake Ontario, Lacus Ontario, in the south, and you can see the red line around it shows how big it used to be. Okay, these things change with the seasons. We have not seen all the seasons on Titan. We've only seen 2 of them. Cassini lasted about that long. So it is a planet moon. Here it is compared to the Earth. And there is a problem with Titan and biology or biochemistry. It's called the T problem. Chris McKay came up with this label, and here's the T problem. It's a cold winter night. You get out your nice cup of hot tea. You dump a spoonful of sugar in, and what happens? It dissolves, it melts. You might have to stir it a little bit, but yeah. Okay, now, 6 months later, it's summertime. You just mowed the lawn. You want to sit down with a nice glass of iced tea, and you dump a spoonful of sugar in, and what happens to it? It dissolves. Not very. It does, but it takes a lot of work to dissolve sugar in something cold versus something hot. Titan is very cold. The temperatures are far below the point at which most biochemistry that we're familiar with can operate. Okay. However, there are momentary hot spots on Titan caused by a multitude of things. One thing is cryovolcanism. We have identified with fair certainty several sites on Titan that are cryovolcanic. Now these are still super cold by comparison to the Earth, but they have to be hot enough that water ice, which at Titan is the consistency of granite, that has to melt and erupt out as lava. It's cryo water. So something internal is heating these volcanoes, and that may create an oasis where liquid water can last long enough to begin some biochemical processes. There are still craters being formed. They're pretty rare on Titan because of all that atmosphere. But when a large enough meteor comes down, makes a big enough crater, some estimates say that you can freeze over the liquid water that results from the impact, and you'll keep liquid beneath that surface for several thousand years. So the problem, of course, is we have no idea how long or even how life arises. We don't know how long it takes. We don't know how it works. Biochemistry is one of the great, well, biogenesis is one of the great mysteries of the universe. And we're filling in some of the blanks, but there's still a lot of work to do. If you know an astrobiologist, one way to get them really excited is to mention vinyl cyanide. They'll just go all jealous. Vinyl cyanide. Why is that exciting? Well, it's present on Titan in its chemistry, and vinyl cyanide actually makes a great cell membrane or a cell wall. It's permeable to gas and minerals, and so when you're looking for life, exolife, life on other planets, you look at the list of materials that are there to see if, okay, maybe this place is a good candidate for life. Titan has a lot of them, has a lot of its own problems, though, much like many of the people we know. So that's okay, we'll cut it a break. It is one of my favorite places, and all of that chemistry is going on some of the weirdest landscapes in the solar system, including this terrain, which is called labyrinth terrain. And the more convoluted you get for the surface, the more interesting the chemistry is. I did a painting here to show what the labyrinth terrain might look like. I have to push my button, there we go. So this is using some Cassini radar and doing a little landscape just to help us dream and imagine what it would be like to be in this bizarre and wondrous world out there. We may have a much better view, much clearer view very soon. 2027 is the launch of Dragonfly. It is a souped up, in effect, a drone. It's an octocopter. It has 8 blades. As I mentioned, Titan has a lot of pressure, a lot of air, and it's got very low gravity. It's got 1/8 of a G, 1/8 of what we have here. It's the perfect place to fly. It takes very little energy to put even something this big and heavy up into the air. And so they hope to explore hundreds of miles of terrain while this is still alive. It's nuclear powered. It's too dark out there for solar unless you're in orbit. On the surface of Titan, you just can't make it work with current technology. So nuclear powered, and it's equipped with all kinds of great spectrometers and gas chromatographs and things to explore what makes Titan tick, especially all that mystery chemistry. And I know that SpaceX has blown up a few of these, but I do have faith that one day someone will come up with a craft to bring us out to Titan, because we are explorers. And that will be a wondrous time of exploration and discovery. Here is one of them. This, I believe, was Starship 2 before launch. So we look back at the Earth and all its different stages, from infancy to teenager to maladjusted adult to present. And we have seen patterns, we have seen climate change, right? And in fact, it's very interesting how the climate has changed in the past. There have been times on Earth that were much warmer than it is today, okay? And we have seen snowball epochs as well. Here's the difference, though. The changes in climate that led to hot periods built over thousands or millions of years. A recent temperature increase, which has been equivalent roughly to many of those rises, has happened in 150 years. Okay, there's something happening here that is on a much shorter scale than this planet has ever seen. And it turns out, if you look at the blue line, it's a little bit cut off there. The blue is human-made carbon dioxide. We can tell because of the isotopes that it's burned material that leads to it. And the green is the background CO2, the normally occurring. They actually line up very well, kind of behind Jack Eastman. Hi, Jack. So anyway, there's a lot of gloom and doom these days about climate change, but I have a great deal of optimism, because some of the greatest minds on this planet are working this problem. While we are stuffing our atmosphere with material that looks a lot like the atmosphere on Venus, we are actually beginning to discover ways of solving some of these problems. Alternate energy sources, solar stuff has dropped like a rock in terms of cost, okay? And it's skyrocketed in efficiency. That's just one of many alternatives that we're looking at. Wind, all of these things have problems, okay? But they've all got solutions too. We're even looking into alternate nuclear energy. For example, thorium reactors don't have the same kind of nasty fallout that plutonium and uranium do. It has its own problems, but we are working on those as well. Fusion, of course, is the holy grail. that if we can figure out how to make fusion work, we figure out how the sun does it. We're echoing the power of our star is the best approach. The key may lie in helium-3, which is on the moon. We're sending people back there through Artemis. There are 30 nations working together to get people back to the moon. And helium-3 is one thing that we're going to be exploring there. All that to say that people are pretty clever, okay? We have had a long time to really mess this planet up, and we have a lot of people now. So we have a great force, a lot of, energy behind some of the movements we have, but we also have a lot of very creative people working on this. And we can all do stuff, there's small things that we can do as we think locally. Take a short shower, don't need as much beef, recycle, okay? All these things sound silly, but you add them up in hundreds of thousands or millions or billions of people, that's going to start making a huge difference, okay? So just some food for thought, some things we learn from other worlds as we cherish this this unique planet, a planet unlike any other world. We have learned from other worlds just how special this place is, and it's fun to marvel at where it's been to get it to where it is today. I think we have time for a few questions, do we? Good. And also, then I've got a lot of books over here. The books about what this was. I have some of my novels, which are from the science and fiction Springer series, and other stuff. I'm selling them at my cost, so and I do accept chocolate in payment. So, questions, comments? Yes. Yes.
Yeah, do you think that one of the periods from ice ages and stuff maybe came from Oort cloud hiccup and threw some comments our way to get us some more? I know, I just stepped out of geology class for this semester, so my brain's some more rain, so. And there may be rocks too. Thanks.
That is just a great question, and in fact, I think it was about 15 years ago, there was this obscure little article in Sky and Telescope about how the Quaternary period, a lot of the ice ages came about as a result of impacts, cometary impacts. So it's not crazy, it's possible. And in fact, I have a friend, Bill Hartman, who is credited with discovering that Mare Orientale was an impact basin. And he said that the best way to understand the moon is through the structure of impact basins. If you don't use those, you miss everything. So I think impacts in general have just sculpted every solid surface in the solar system. And of course, they contribute to the chemistry of the gas and ice giants as well. So yeah, not a crazy idea at all.
Do you think that we are missing something by assuming that the only form of life would be identical, in terms of its history to us, or, the wildlife on Earth now? I mean, that seems pretty narrow. I mean, there are lots of things that could start cyclical chain reactions and eventually maybe evolve. So I mean, what we're saying, we've got to have a certain amount of oxygen, certain amount of CO2, a little bit of nitrogen and all that. It seems like we could be missing something with a different past.
Yes, absolutely. Now, but so here's the problem. for exobiologists. Let's say we assume that there's silicon-based life. Well, we can't test for it. All we understand right now is amino acid DNA-based life. And so we have to use that as the first step. I think most astrobiologists will say, yeah, there's bound to be other things out there. There are complex chemistries, even just right here at your robot going on that are very different from Earth's oceans that may have led to life that's quite different from what we have here, based on other things, exoplanets, the stuff we're finding out there, the variety of environments, and yet the rich chemistries that have virtually nothing to do with Earth's history biochemically. The possibilities are astounding, but we're taking baby steps. All we can do right now is look for life as we can recognize it. Viking, way back in the 1970s, 1976, had an experiment that I thought was brilliant. They turned the camera on, and it was a little scanning camera, and they just let it stare at a piece of the ground. If anything moved across it, it would make a line across the image. And it was great because when they tested it in parking lots and stuff, it picked up ants and ladybugs and all these things, stuff that you're not making any assumption about the life except that it's moving. So I thought that was very clever. So astrobiology has come a long way since the days of Viking. We know better questions to ask, and we have better instrumentation for searching. But we're still just just getting started on that great biogenesis question. So
I see Mike Gardner online has a question.
Oh, thank you. Very interesting talk and quite a bit of good information. During your introduction, you mentioned something about the location of a star system with planets within a galaxy, and that might have something to do with the development of life. Can you explain that or go into a little more detail about how that system or that mechanism might work?
yeah, I mean, we are not quite in the Orion spur. We're kind of in between a couple of streams of stars. If we weren't, radiation levels here would be really high. Radiation is just one example of why location is important in a galaxy, but the stellar population changes as you move from the hub of the galaxy out. And so it's possible that the further out you go, the more you begin to lose some of the building blocks that are essential to make a planet with the Earth's environment. And likewise, as you go in toward the center, things change chemically and in terms of radiation because you've got more densely packed stars and stuff. So I think that's mainly what they're talking about.
What was the vinyl item that you mentioned?
Vinyl cyanide. Doesn't that sound great? I want shoes made of that.
I noticed that about that point in the talk, there was some terrain that kind of looked like Naugahyde.
Mere coincidence? I think not.
This might be a little bit off the subject, but one of the things I noticed when you were going through the extinction events, okay, directly before the Cambrian period. Okay, and my question is, since you've obviously done a lot of research into this, have they come up with any type of an idea to trace how the Cambrian explosion occurred?
Oh, isn't that great? Yeah. I haven't dug into that very much. I've done some surface reading. I do know that there are multiple theories, and they're loose in terms of data. And we're talking a very ancient event.
There's a branch of very fuzzy science, I believe called cladistics.
Yes, right,
That has tried to trace everything.
Yeah.
From Precambrian period up through the Cambrian explosion.
Right.
It never, without any fossil record, it's always been a puzzlement.
That's the problem, but you know, the paleontologists believe just because of patterns in history that the longer we go, the more we'll find, the more data we'll get.
It's just never happened though.
Not always, I know, but yeah, it's fascinating questions about the start and almost stop of life throughout the history of our planet. And when you look at some of the dynamics of exoplanet systems, it's even more hairy. It looks like you could plop a nice Earth-like terrestrial in there and give it a few million years and it's gonna just keep getting wiped out, you know, from various things. We need more, I love to say this, we need more information. We have to keep exploring. Yes.
First, I love your speaking style, good energy, positive. Really love that. What's your position on extraterrestrials? Communication, stuff like that.
Yes.
And especially those things at the Pentagon, those fuzzy little.
Right, the
Drone
things,
looking things, yeah.
yeah, that have recently been, right. I've actually worked with art directors who make me believe in alien life, but that's another story. You know, the numbers are astounding, obviously. That you just take a glance at the Drake equation or something, you see how many Earth-like planets there must be out there. And in fact, there are probably more than we initially thought. Earth-like is not Earth, however. There are going to be issues in a red dwarf system where we found most Earth-like planets. They have to orbit so close that they're going to be tidally locked usually. So you'll get high radiation on one side, frozen atmosphere on the other. So is that Earth-like? I don't know. It's hard to find a planet like ours. I think personally that if there are things out there, civilizations, they will visit us with technology that we really don't understand. We are missing something in terms of quantum physics, the structure of the universe. We can't travel practically to the nearest star. Well, you can get there in about 50 years if you use a laser sail. That's the current estimate. That's pretty crummy. The reports of UFOs defy the physics that we understand, certainly defy Newtonian physics. So I think that if there are things out there, they're probably operating with technology that is so different from our experience that we may get glimpses of them, but that's about it right now, unless they really want us to have a chat. So it's intriguing. You have to ask yourself why there would be so much space, empty space, devoid of life. When so many planets are designed to have the building blocks of life. So that's what makes me think that somebody's out there having this discussion with a much more talented speaker somewhere.